Okay, merci. Yeah. Thanks a lot, Yvonne, for the introduction and the invitation, of course, to come to Paris here, which, I mean, gives the opportunity to meet a number of old friends whom I have known for a long time. What I will be talking about today is dipolar gases and the connection they have with supersolids. This is a field which started about 20 years ago with the achievement of Bose-Einstein condensation in chromium by the group of Tillmann-Pfau in Stuttgart. And it has sort of taken off then years later when other isotopes of rare earth atoms were Bose condensed. In 2011, in Innsbruck, Rudi Grimm and Francesco Falerino, and at the University of Illinois, namely sort of the original BCs were with chromium, but the one with really strong dipolar interactions are the rare earth materials erbium and dysprosium. And in particular, sort of the field really has become extremely interesting after, in 2016, Igor Ferry-Barbu, who was a postdoc at that time in the group of Tillmann-Pfau, discovered that in these systems there is actually the formation of self-bound droplets. So the attraction with dipolar gases leads to droplets, so we are going from gases to liquids. And then later also sort of in a way to solids. So in a way, dipolar gases allow you in a way to cover the whole range of things that you know in condensed matter physics. But as you will see, is the theoretical description of these systems is quite difficult, and it's, I would say, the state of the art is rather superficial. So what type of interactions do we have? We have interactions which we assume to be just sum of two-body interactions. And there is a short-range interaction, which we assume, as usual, to depend only on the relative distance, rotation invariant. Then there's, in addition, the dipolar term, 1, 2, which is long-range and anisotropic. And the trivial, more or less trivial part is the short-range part. The short-range part I will represent by a pseudo-potential, such that in momentum space, that's just a constant. This constant is assumed to be throughout positive. So that's positive scattering length. That's a sort of, as we believe, a stable BC. The dipolar interaction can be written in the following way. It's minus d squared divided by the 1 over distance cubed, this typical dependence on distance of interaction between two dipoles. And I will assume these two dipoles to be point dipoles. Of course, there is, you see, a singularity at the origin. I have to cut that off, and that, so that's a cutoff which eliminates the short distance singularity, which I mean, and then there's a function which I denote by d12. That's sort of the angular dependence. And I write this in general in the following way. The d12 is 3 times, so this is just the L equals 2. Direction of dipole 1 dotted into the R12. Direction of dipole 2 dotted into R12 minus the scalar product of the two directions. That's the most general form which I have for the dipole interaction. Now, in dipolar gases that have been looked up so far, these dipoles are all oriented. They're all pointing in the z direction. So basically, if the dipoles are the d's is always the z direction, independent of which dipole I'm looking at. They're all oriented. So then this function, the d bond 2, goes over to 2 times the Legendre polynomial of d, or times R12. OK, so that's the dipolar interaction. And you see, if I look at what the total interaction is as a function now of momentum, then OK, let me first, total as a function of momentum. Then I can, in a way, pull out the constant term from the short-range interaction and write it as 1 plus, and then there's a crucial strength of the interaction, which is called epsilon dd, where epsilon dd is a characteristic length associated with the dipolar interaction divided by the short-range scattering length. That parameter will always be positive. And as we'll see, things get interesting when this epsilon dd becomes of order 1, or in particular, it becomes larger than 1. Then the dipole interactions are appreciable. In chromium, originally, sort of this epsilon dd was on the order of 0.15 or so. You could treat it perturbatively. But that's no longer true in this case of the erbium, and in particular the dysprosium condensates, where you have sort of magnetic moments on the order of 10 mu Bohr or something like from the unfilled shells. So what is, and the question is, I mean, if I Fourier transform 1 over r cubed with this Legendre polynomial, what do I get as a Fourier transform? Well, 1 over r cubed has the same scaling dimension like a delta function. So there's no dependence on the magnitude of the wave vector. So this is just 2 times p2 now of d times q. And so where the epsilon dd, epsilon, I can write I can deduce a gdd, which is the product of g times epsilon dd, which is just 4 pi d squared over 1/3. That's a quantity which you can formally relate to a scattering length for dipole-dipole interactions, but please do not confuse, there is no scattering length. Dipole-dipole interactions have no forward scattering. So what I point out is that the V dipole-dipole at q equals 0 is 0. There's no, so this is, of course, depends on, I mean, introducing this, it's an improper integral, you have to deal with this properly. From the angular average, this is just because the angular average of the dipolar interaction vanishes. If you have a regular, if you have regularized it at short distances, that will play a certain role. Now you see this interaction is quite of a nuisance, and sort of, I mean, mathematical physicists will not treat it because, I mean, you cannot prove anything on it because it's, from a mathematical point of view, it's ill-defined. Well, it has the following sort of nasty things. A, it's not rotation invariant. Well, that's a nuisance, but it's not something that would bother you seriously, but it has some interesting features. B, it's partially attractive. That's a disaster. Bosons, I'm only talking about bosons here. Bosons with attraction, I mean, that's sort of something that's collapse. We will see that, but of course, as I mentioned here, sort of but of course, if you average over angles, the V dipole is 0. So it's repulsive and attractive sort of on both sides. On average, it vanishes. And it is, as we will see, this has sort of really very peculiar consequences. It is long range. One of R cubed. That's a type of interaction which, I mean, is quite difficult to treat. So let me before that, if I look at this interaction and I do something very naive and say, okay, let's just do Bogoliubov theory. Then in Bogoliubov, if I treat this in Bogoliubov, then I get a dispersion law for excitations around an assumed condensate, which is an assumed condensate density times epsilon q times V of q. Epsilon q is all but the free particle dispersion, h bar q squared divided by 2m, plus the free particle dispersion squared. So that's a simple Bogoliubov formula. So if I go to small momenta, then this term is irrelevant, and I go to h bar squared c squared of q times q squared. And you see the sound velocity which you get for these systems depends on direction. Namely, just it's the sound velocity squared of what I call is the normal short-range interacting gas squared times 1 plus epsilon dd times 2 p2 times as a function of d dot d. So you see, if I propagate sound along the long direction of such a gas, it is stiffer because the Legendre polynomial is positive if the argument is 0. But it's softer if I propagate in the plane. I assume sort of in a way spheroidal geometries. So I have rotation invariance still around C, but I have not full rotation invariance, of course. And I've broken full rotation invariance, of course, by the external field. So it's not spontaneously broken. It's just with the external field. And so this becomes, so this is a factor of 1 plus 2 epsilon dd, so that's fine. So it becomes stiffer in this direction. But then it minus epsilon dd for q perpendicular to d. And then you see this is already disastrous. I mean, that it means that sort of there's this system doesn't have a sort of proper compressibility for compressions along sort of this directions. So if I compress the system here in this direction, once the epsilon dd becomes larger than 1, you're gone. I mean, the system is unstable. So the conclusion is, and this is something that, I mean, okay, I would like to sort of in a way show rigorously, but I think it's kind of obvious. So one of the conclusions is sort of there is no homogeneous dipolar gas with epsilon dd larger than 1. But everything interesting for us appears there. So actually, the anisotropy of the sound velocity has been measured by a group at Villard-Hinault in 2012 for chromium. There, the anisotropy is on the order of 20% or so, and everything is fine. But I mean, in the strongly interacting situations with erbium and dysprosium, this is not really stable. Now, let me add something.
Is there an estimate of how much the PDD is for erbium and dysprosium?
Well, I mean, you crank it. Of course, I mean, you cannot change the strength of the dipoles they are given, but you can change the scattering length. And so, I mean, people have gone up to around 1.5 or 2. Not actually sort of, I believe that if you really go beyond 2 or something like that, things become sort of completely disastrous. So you stay away from that. But, okay. Yeah. So exponentially, in principle, you can go to infinity, but I mean, it makes no sense physically, I believe. Okay.
Are you saying that you see the instability experimentally also if you go to very high Epsilon?
There have been instabilities have been seen. It's not, but I think this has. I mean, I'm not familiar with all the literature, but I mean, people haven't. I mean, it's known that this system becomes unstable eventually. I mean, this, as far as I know, hasn't been investigated in detail. I think it's not that interesting, but oh well. Okay, now let me come to the long-range part, which is quite important. So, and start with something very basic. I mean, in equilibrium thermodynamics requires that if you have a system in equilibrium and you describe it by a free energy, then you have the usual story that the free energy depends, for a fluid, depends on temperature, volume, and particle number. But in a way, of course, we always assume that, okay, this can be written as n times a free energy per particle, and a function, an intensive function, which depends only on the volume per particle. So this is the first assumption, plus corrections which go like the surface, n to the 2/3 or something like that. And, of course, with two properties, namely this f tilde is finite, and b f tilde is shape independent. It shouldn't depend on shape. Otherwise, typical thermodynamic arguments don't work. To prove, I mean, if you take an ideal BC, both properties are not valid. So it was the paper which you mentioned by Dyson in '57. So Dyson was the first to be aware of this, that there is a problem here, that the ideal BC fulfills neither A nor B. The ground state wave function of a BC depends on what type of boundary conditions you make in your box. And the energy doesn't go linearly with particle number. It goes linearly with particle number, but it scales like 1/L squared and not 1/L cubed. Okay, so Dyson proved that, I mean, it's fine for hard sphere bosons. So that's fine. But then the question is, I mean, what type of things, I mean, what is sufficient for having this? Well, I mean, this was proven in whatever, first by David Ruel from the EIS in Bure-sur-Yvette. In which direction? I'm not sure, but he's still alive. I mean, this is one of the remarkable papers. He proved that if you have short-range interactions decaying faster than 1 over r to the cubed, and rising faster than also 1 over r cubed at short distance and being sort of bounded below, then this is fine. And also Michael Fisher sort of. I mean, so these were things in the 60s. But for the long-range interactions, I mean, things were not so easy. So, and this has been mentioned by Mathieu yesterday, so A plus B both hold for Coulomb or dipolar interactions if, well, the stuff is neutral. All the QJs add up to 0. Then it's fine, and you actually get exponential screening. Or in the dipolar case, respectively, the sum of the dipole moments is 0. I will not go into these proofs or so. I'm not. But I mean, for the dipolar interactions, it was actually proven by Griffiths in '68, and then by Jörg Fröhlich in '78 or '79. So these are quite hard problems. And these are extremely important papers. I think they are sort of about the fundamentals of sort of the thermodynamics and many-body theory, and essentially beyond the community of mathematical physics, it's essentially unknown. It's strange. I mean, you know, this is water. Is a dipolar fluid, permanent electric dipoles, and I will come back to water. And you want to make sure that the thermodynamics of water doesn't depend on shape, and you have to convince yourself. But here in the dipolar gases, with all the dipoles the sum on all these dipole moments, which I can write as an integral over a magnetization, is just the number of particles I have times the dipole moment d of a single atom, times they are all pointing in the C. This is extensive. And you are not going to have shape-independent thermodynamics. Sure. You have to deal with this. So it's not a simple problem. OK. Honestly, I mean, in hindsight, dealing with sort of shape-dependent thermodynamics is something that, I mean, we have known more or less for a long time in sort of demagnetization factors of spheres or something like that. So let me come to this. Namely, I want to, first of all, I write the dipole interaction. That's the one which makes the problem. You can write this formally in the following way as -1/2 the integral over mc of x as an operator times bc of x, the c component of a magnetic field, also as an operator. So you can write this in a way that is familiar perhaps from sort of magnetostatics, where this magnetization operator is just d times the one-particle density operator. That just tells you magnetization is dipole moment per volume. That's all. But you have to be cautious. Of course, there's a product of operators here, and we cannot replace this product of operators by sort of the product of expectation values. This you can do in mean field theory. So if you treat this in mean field theory, then you get a problem which is in a way the one which you learn in magnetostatics, that you say, oh, you have a given magnet. Let's assume we have this gas in a trapped situation. We have some density profile. Then we know the magnetization. What's the magnetic field produced by that? If you're outside of this, then you know, I mean, it will eventually always create a dipole field with the total dipole moment of this thing. But of course, we want to know it inside, because this BC of x is the magnetic field at point x generated by all the other dipoles surrounding a given dipole at point x. And and one sort of well-known problem is you take a sphere with homogeneous magnetization. That problem is treated nicely in Jackson. You have there are some magnetization currents running around in an azimuthal direction, and they produce a field which for a sphere is actually perfectly along the c direction here. And the way to treat this is to say, well, we know the magnetic field, we write the magnetic field as H plus M, so the H field, the Hilfsfeld, the help field, plus the magnetization, and we want to know what is the help field. Well, in a situation with sort of a given magnetization, there is something which is called the demagnetization tensor, and I write tensors with a bar, with an underbar, times the magnetization. And this demagnetization tensor is for a sphere, because of rotation invariance, is just 1/3 times sort of the unit tensor. And then what you get is this gives you an inner field. This predicts you an inner field in the center of such a cloud to be 2/3 times the magnetization. So that looks nice, but there's a catch here. This result is not the full, or that's not the correct result. The correct result is it should be 0. Why? It is 0 because we have to not include this. We have to have a cutoff at short distances. This comes from the delta function contribution to those. If you look at what is the magnetic field of a point dipole, then this is 3 times d times r times r minus d divided by 4 pi r cubed. That's it. What you would usually write down, but if you are careful and you know about hyperfine interactions, you know that the magnetic field of a point dipole has a delta function contribution. Namely, it's plus 2/3 times d times a delta function. So mathematicians, forgive me to introduce a delta function here. It's neither liked by mathematicians nor by experimental physicists, but I mean, this is, so the physics, and this is something that this now at the moment has nothing to do with dipolar gas, or has, of course, something to do with dipolar gases, but it's pretty important that many people don't know that. And if you sort of do the same thing, so this is the plus here. If you did it for electric dipoles, there would be a minus 1/3 here. So why that? Well, very simple. take two dipoles, two magnetic dipoles, and go away from the delta function and say, okay, there's some current, small currents flowing around here. And there's another dipole, a magnetic dipole, nearby, also has the same current direction. What's happening if I get those close together? Do they attract or do they repel? Well, they actually attract. That's this part. Because actually then these two dipoles form together one with a larger current through it. Do the same thing with electric dipoles. So I have a plus minus here and another plus minus here, and get these guys close together. They repel like hell. That's it. And that's the reason for this difference in this sign. And it's actually sort of interesting, like, I mean, as I mentioned, it's hyperfine interactions. If you go to the, whatever, for instance, simplest case is hydrogen. What is the effective hyperfine interaction between the electron and the proton in hydrogen? There's some, what I will call an exchange coupling constant. And this is, turns out to be about 1.4 gigahertz and is positive. So then you say, wow, is it that not contradicting what I said before? I mean, because that means that in hyperfine interactions, it's the singlet state of the, which is lower. But the product of the gyromagnetic ratios of the proton and the electron have opposite sign. So the magnetic moments really stay parallel, are parallel in the hyperfine ground state of hydrogen. And that's sort of this picture for that. So, but as I said, I mean, I want, sorry.
You're trying to use that argument to explain the change in sign between the magnetic and the...
Yes.
But I mean, in classical electrodynamics, all you need to do is to take the limit of finite dipole moments, which you can do, of course, for...
Well, I mean, this is, I mean, it becomes, I mean, to really calculate sort of the interactions between extended dipoles is some sort of, requires some calculation. It is done in a nice paper by David Griffiths, so you can look it up there. Okay, so we have to subtract this off, but this is something we don't want. We don't, although these are bosons, they sort of, the short range interaction in a way must be such that at short distances, it's only short range. And the dipolar stuff, we have to, in a way, suppress that at short distances. So we have to subtract that. And then if we subtract this, then if I calculate the product of dipole moment times magnetic field, which is an energy, then what I get is that this is the product of is d times one-third m. And so here, there would be the full m. See, that would be the full m that I should do. But subtracting this 2/3 makes this here. And then if you do this, then you can, I mean, as of x, and in some mean field, in a mean field approximation, you can write this as this interaction constant GDD times the density of x, the local particle density, times, of course, the c direction. Magnetization is in the c direction, times And now the factor that comes in here is from this 1 minus 3 times the C component of the demagnetization tensor. This function has been called f of kappa. The demagnetization tensor is shape dependent. It depends on the shape of your spheroid. And there is an expression for this demagnetization factors for spheroids. You can express them in inverse hyperbolic tangents or arc tangents. You can look it up in Landau-Lifshitz. It's actually not in Jackson. Jackson only treats the sphere, but you can look it up in Landau-Lifshitz 8. And this is a function which looks like the following kappa. If kappa is going to 0, this means I'm looking at gases with very prolate shape. Then there's basically no demagnetization there. That's the usual story. There's no demagnetization in prolate shape. And then this F goes to 1. Then it goes down to 0, and it reaches minus 2 in a strongly prolate case. There, I mean, basically you have arranged all your dipoles which point along C in the plane, and then so they produce sort of the opposite field sort of for the other dipoles, and then this becomes sort of strongly repulsive. And so this goes linearly through 0. So this is actually this function f was introduced in 2001 by Li and Yu, coming from some Gaussian approximation to the Gaussian variational answer to the thing. And I mean, in all of the literature, the whole literature, I've never found, and I think people are simply not aware of it, that this function is simply the demagnetization factor of spheroids. That's all. Okay, good. So now the question is, I mean, okay, this is in a way already doing a mean field. I'm treating this sort of as a given magnetization. So here in this, I say, okay, I can replace this by a given magnetization, and there is something where this magnetic field, the produced magnetic field is also a C number. So the question is HDD at kappa equal to 1 true beyond mean field? So does it average out always? Or even for a spherical configuration? Oh, you're good intuition. It's not, no. And the one way to see this is something that there's a truly remarkable paper by Monsieur Wertheim in '71, actually on the proposal by Joe Leibowitz. Joe Leibowitz proposed him this problem, who actually treats water as a dipolar fluid, electric dipoles, randomly oriented, as a classical fluid of hard spheres with point dipoles. And so I will not say too much about this, but I mean, what he says is, okay, now, if I look at what's happening beyond mean field, I have, of course, to represent my pair distribution function not just by 1, but a non-trivial pair distribution function. So the function G2, you have two dipoles, 1 and 2. And you subtract the trivial limit in a fluid that, okay, at large distances, the pair distribution function goes to 1. This is often called the pair correlation function, the H function. You can, and this goes back to Wertheim. There is a piece which only depends on distances. But that's not all. There is a piece which is called HD, which I mean he called HD of R on 2 times this D12 I introduced up there, where the pair distribution function follows the interaction. So I mean, these guys, in a way, of course, they prefer sort of, in a way, the configuration where they are sort of going into this direction. I mean, that's this function plus a function h delta of R12 times D1 unit vector times D2 unit vector. Now, this piece we can ignore for the dipolar gases because, I mean, this is always unity, so we can write this here because it's a rotation invariant. But this piece is not. That's there, and that sort of gives you a preferred orientation sort of these guys in the pair distribution function. And it turns out that, so if you look at the energy per particle you have, for instance, I mean, in any of such, in such dipolar fluids, with the short-range stuff of point dipoles be subtracted, is minus times GDD times N times, and so there's an integral dr hd of r divided by r. That's all. That's the piece which, I mean, gives a finite contribution to the energy. So the people in Gross-Pedevsky, nothing is there. I mean, this is completely, there's no HD. But of course, it's there in principle. This is a dimensionless number. And this has been calculated by this guy, Wertheim, for hard sphere gases, dipolar hard sphere gases. And actually, he was able to explain the dielectric constant of water with that. It's a truly amazing paper, solving some 3 coupled integral equations for these functions. But now, and so this is non-zero, even for sort of the rotation invariant, for a rotation invariant situation. What happens if I apply this to cold dipolar gases? What I can show is that this HD of R has an interesting behavior, namely, it goes to a constant divided by 1 over r to the 4th at large distances at 0 temperature. Actually, so there's an exact result which I've derived perturbatively in the interaction, where sort of you don't have this problem with the instability. And at finite temperatures, it goes like essentially kBt divided by GDD n times divided by 1 over r cubed at finite temperature. And the important thing is this function is positive. See, if you look at the pair distribution function in a Wiki interacting BEC, then, I mean, you know, okay, out there, so this is the 1, this is the G2 of r, this is minus 1 over r to the 4th, and then there is a short distance behavior which is governed by the two-body wave function. Here, this HD function, which, I mean, makes all the effect in usual polar gas, dipolar gases, I mean, comes from above. That's positive. And that gives rise to, so that's actually, so this is an interesting point, which I actually discussed a bit with Jörg Fröhlich, but I mean, to really show something rigorously here even is very difficult. This is an example of a correlation inequality. In sort of correlation functions cannot decay typically faster than the interaction. If the interaction decays like 1 over r cubed, you cannot have correlation functions which decay faster than that. Okay. So the final thing in this context is you can, I mean, perturbatively for small epsilon dd, this thing for epsilon dd less than 1, where I'm on the safe side with, well, having a positive Fourier transform, at least of the potential, I can show that the dipole-dipole interaction per particle has the form minus epsilon dd squared times g times n times na cubed to the power 1/2. So the leading term in the interaction, if you do it for a homogeneous system for small epsilon d, is LHY-like, but with the attractive sign. It's not a positive one. And that's something that, okay, I mean, the whole community is not, this is something that is beyond what anyone has looked at so far.
Can I ask a quick question? So we're talking about the Wilhelm stuff. So there, the water street is classical dipoles. Am I right?
In water, yeah, you have just a classical dipoles.
And of course the results you're referring to here are not for classical dipoles at 0 temperature.
Well, see, I mean, this result holds also for quantum dipoles. So that's a completely general result.
Okay, so just I just want to make sure that.
But you're saying it also holds for classical dipoles?
Also, yeah. So, I mean, of course, I mean, the HD is a different function, of course, but I mean, this is the same function. It's just the decomposition of Mr. Wertheim.
Yeah, because I mean, in classical dipoles, let's say the water, at some point, the water itself is going to go into a ferroelectric phase transition.
Okay, yeah, this is beyond this model. I'm not, see, I mean.
So the t equals to 0 limit is going to be.
No. I mean, of course, like, I mean, the Wertheim is not considered with this. I mean, this is the classical gas. Classical hard-sphere gas with point dipoles. And that can be in the so-called mean spherical approximation due to Joel Leibowitz. He could solve exactly. And he got a result for the dielectric constant of water, which is around 30. That's not 80, but it's not so bad. Actually, if you take the model seriously and do numerics on it, and this was done only in 2006, you get 75 instead of 80. So the remarkable thing is that a super simple model for water, hard spheres plus point dipoles, with the known density of water and the known strength of the dipole moment, gives you within a few percent the dielectric constant at room temperature. I mean, these things are, okay. I mean, I recommend the book by Jean-Pierre Hansen and Ian MacDonald on the theory of simple liquids. It's all classical. But
you said that this was analyzed for the quantum problem as well.
Well, I mean, this is what I did myself. I mean, it's not a big deal. I mean, you can just transcribe it. So let me discuss equilibrium in a trap. That sounds super simple, but this is not so simple in this case. What I claim is that, okay, I mean, the condition for equilibrium can be written in the following way, that the divergence of the momentum current tensor is, so this is in a way if you wish, roughly the pressure of the system. I mean, the pressure of the system must be, of course, balanced by the external force. And the condition in general can be written as a divergence of a tensor, which is a vector, is equal to the external force, which is minus n phi of x times the gradient. So this is the trap potential. The n phi of x is the equilibrium distribution in a given phi of this potential. So the major question is, I mean, what is the equilibrium momentum current density in a fluid which is uniaxial? And the answer is, this is it has no in equilibrium, it has no off-diagonal components. Actually, if we had a quantum Hall system, you can have off-diagonal components of the stress tensor even in equilibrium. That's the so-called Hall viscosity. But you need PT violation. Here we don't have that, so this tensor is diagonal. And for a situation where I sort of have rotation invariance around C is but it's not the same plus, and there is a new function which comes in here. There's an anomalous contribution to the in the momentum tensor, which makes sort of the x and the c components different. It's not a big deal. I mean, it comes from the fact that I've externally broken this symmetry. And what can I say? How can I define this h of x? So there's a, if you wish, a trace anomaly. The trace of pi minus of x minus 3 times the pressure of x is minus h of x is non-zero. Usually, sort of, we don't care about sort of, I mean, you immediately replace this by the gradient of the pressure. But that's, pressure is not, I mean, you have to be very cautious in this anisotropic system. What is pressure? I will come back to this. So what is, how do I define this pressure here? What I look at sort of at the phenomenological level, I mentioned sort of the free energy density or free energy per particle before. And I showed or I argued that for the usual thermodynamics, of course, this free energy per particle, free energy density, depends on volume per particle and temperature, but nothing else. That's not true here. You need an additional, a new variable, a new thermodynamic variable. Namely, and it's convenient to express it in terms of a strain tensor. So I pretend if I'm in a solid, but I mean, of course I'm not, I'm still in a liquid. There's no shear forces. And a UCC, that's the new variable here, which you need in thermodynamics to define it. And then, I mean, there's a minus, so this defines the minus P d trace U. That's the usual story. dF is minus P dV. D trace U is just a local volume change. But then there's an additional term, so this is this P here. And then there's an additional term plus H d UCC. So that appears in dipolar gases because of this broken time reversal invariance. And what you can, so this in particular leads to the following thing, that if I look at a free energy at a given T, V, and N, then there is a term H1 DLC, where this DLC it's just divided by just a local extension. So I locally expand this, and then there's a change in free energy. And the fact that LC, the length of this gas, appears as a new thermodynamic variable is, in a way, you have a second independent extensive variable in the system. Gibbs theorem is violated. So Gibbs theorem is violated whenever you have an extensive variable in addition to, I mean, what you usually have. The standard case is sort of surface tension. Then you have the area. But then in the surface tension situation, then you can say, well, the area term sigma dA is actually on the order of volume to the 2/3. So in the thermodynamic limit, well, I don't care. Here, it turns out that this beast stays there even if I take the limit n going to infinity. This is because of these long-range interactions. So this stays whenever there. And the most important thing is this h1 turns out to, is just the, sorry. So the h1 is just the integral over the h of x over the transverse degrees of freedom. So I perhaps should write this as x, y at, if I do it locally, x, y, c, integrated over dx dy, so I integrate over sort of a plane. This is negative. And this just says this system sort of, I mean, it's very simple to understand physically. This system likes to expand along this direction because then it can sort of align your dipoles in a favorable situation. So there's a spontaneous sort of negative line tension here. And it's, in a way, limited only, of course, by the trap. I mean, unless if you don't have a trap, this stuff, I mean, in a way, wants to go away, just disappears. Okay. Actually, I think in view of the time, I will omit this. Actually, there are nice things here. You can actually, there's an experimental, so this is, okay, let me mention it. If you can do you can measure the density distribution and look at the integrated sort of n tilde of c. You integrate the density at a given cross-section over the transverse direction. Then this, and if you can do in situ density measurements, then in principle you can access to that. And then there's a simple relation, namely this thing is actually in a harmonic trap given by 2 pi over m omega x squared times pi xx 0, 0, c. So this funny sort of components of the momentum current tensors can be measured. That just comes from the equilibrium condition, hydrostatic equilibrium. This is a relation which I think many people have used, Christophe Salomon, many people have used to, in a way, infer what they call pressure. Here it's this thing from in situ density profiles. And you can now, but if you take now the derivative of this, dn tilde of c with respect to c, so this formulas go back in this form to Jason Ho and Su in 2009 or so. There's a term which is minus 2 pi times omega c squared divided by omega x squared, just sort of the ratio of the trap frequencies, times c times n, let me see, it's in phi of 0. So that's the formula which they derived, and it's a formula which in a way follows from Gibbs theorem. But there's an additional part now because of this H field. So there's a plus 2 pi over m omega x squared dc h of 0, 0, c. So that's, you see a variation of Gibbs DM. So Gibbs DM was a French engineer, in the late 19th century, and it's nice to read the history. Apparently he had some sort of strong arguments with Marcelin Berthelot, the guy at the entrance of the Collège de France. Okay. Okay, and finally, well, two exact formulas which I want to write here. You can see, I mean, okay, now I come, this is important. I mean, all these things, in a way, ask you, I mean, how can I define pressure properly on a microscopic level? There's a nice paper by Paul Martin and Julian Schwinger in '59. Namely, you do so. Can you write down a pressure operator microscopically for a many-body system? And what they say essentially, so I'm now reformulating it in the way I like it, I do the following. I make a scale transformation, x going to bx. I just rescale my lengths with a uniform factor b, or all my coordinates with uniform factor b. And then I ask, and I let b close to 1, so an infinitesimal uniform dilatation. Then the formula which, okay, is you get is just that the trace of pi of x, the trace of this momentum tensor is just minus d, you take the Hamiltonian density, if you wish, as a function of x, the expectation value, with respect to b, taken at b equal to 1. So that's an exact expression. Tells you that, I mean, the trace of this momentum current tensor can be determined from sort of, if you know how does sort of the energy density behave under a sort of uniform dilatation. Of course, if I write this h of x here, this doesn't, I mean, whenever we have interactions, this is not a local thing. And then you have to sort of make arguments. Can you rewrite this into a local expression? That's another method which I will not mention here. Here, in this case, with dipolar gases, we need a different second independent scale transformation that gives you this H field. Namely, I make the following. I rescale my length along the z direction with a factor theta, and I rescale x and y with 1 over square root theta. So this is volume preserving, obviously. And then there's an exact expression which allows you sort of to express this field in terms of microscopic quantities, namely as a derivative of the expectation value with respect to theta at theta equals to 1. And you can sort of, in a way, rewrite it in terms of the following as minus 3/2 d by d log kappa of h of x. Because you see, you just need to realize that under such a scale transformation, of course, I change kappa. I change the ratio, the aspect ratio, by a factor minus 3/2. And so, in principle, and you can give exact expressions for these things. These are exact relations. In the in the mean field limit, then you recover something that was used before in a nice paper by Claudia Eberlein and Gervasio and Dell in 2005. But I think they didn't, appreciate the generality of the whole story. And finally, okay, I just add one thing on the virial theorem. You all know the virial theorem, and the most, in my mind, the most elegant formulation of the virial theorem is to say, it states the following, that in eigenstates of a total Hamiltonian, which is the total Hamiltonian of the system plus the Hamiltonian of a trap or a box, whatever you like, the box potential, this expectation value is 0. Of course, that's true. If you have eigenstates of this, then the expectation value of a commutator is always 0 by here. So that gives the virial theorem. What you actually need, and this I will miss, is you can generalize this to the following, that you do not take the uniform dilatations here. You take a dilatation, the tensor of dilatations. There's a tensor. And then you get a generalization of the virial theorem, which you can write down, and which involves this H function for dipolar gases. So that's, in a way, roughly the stuff which I can say, joking a bit, Yvonne forced me to learn and expand and develop when I prepared this lecture, because I didn't want just to, in a way, repeat stuff that is well known. Now I should come to the points with, now let's see what I've just 20 minutes. 23, okay. Let's, oops. The really, and I think this is, if you could hand out these things. I've prepared, 2 sheets from a talk I gave last November at the University of Illinois on the honoring Tony Leggett on supersolids, and 2 of the sheets which with some experimental data on it, Yvonne will distribute, so you can have a look at how the experimental results look like, and what perhaps the challenge, what the experimental results are. Of course, I will not really go into the. So yeah. Just yeah. So this is the, in a way, part 2 of the talk, where I will say something about self-bound droplets and LHY. If you recall, I calculated in the beginning this internal magnetic field for the sphere. And I showed that this d times bc in the x near in the center is gdd times the density in the center times 1 minus times this function f of kappa, which came from the demagnetization tensor. And this f of kappa had this form, such that for the prolate case, which is indicated over there also, it's positive. And what does it mean? Now, what it implies is the following. If I look at what is the equilibrium, and now again the equilibrium condition is you know that if you have a system, then you know that equilibrium is realized if the chemical potential is uniform. There's no gradient in the chemical potential. What is the chemical potential for such a system of dipoles? Now, the chemical potential, you know it from charged particles. The chemical potential for charged particles has an internal part, if you wish, and sort of the Q times electric potential. Here, the same thing. Here is the mu of x for dipolar gases. It's just mu, if you wish, which is associated with the short-range interactions, minus the Bc of x. That's, you could call it a magnetochemical potential. It's not used this form, but that is it. If you have dipoles, I mean, they don't move if sort of, I mean, the gradient on sort of other interactions plus the force on the inhomogeneous magnetic field, they cancel out. That's true. But now this is, so if I go to the trap center and I add this, then this gives G times n of 0, just doing mean field here for the short-range interaction, times 1 minus f of kappa times epsilon dd. And you see now there's disaster. If this is, so there's a G effective in the presence of dipolar interactions is G times 1 minus epsilon dd f of kappa. And as long as this f of kappa is positive, this can go to 0. So it becomes negative if epsilon dd is larger than 1 over f of kappa. If kappa goes to 0, then, I mean, you go to the uniform situation. Then you get this instability with negative chemical potential at epsilon dd is equal to 1. You see in the trap, it's a bit delayed. The f of kappa is less than 1, but it's still there. So that's, and then, I mean, the system, so this is not, so it's not, no. So the system is no longer gas. And what do we do? Well, I mean, it turns out, and this is sort of what was discovered by chance. Actually, I talked to Igor very, this was not, they had not looked for that originally. It forms nice droplets with a few thousand or 1,000 particles, nice droplets. So self-bound droplets are formed. And the question is, I mean, what at I call it liquid density n bar, which is about 2 orders of magnitude larger than the density you have in the gaseous phase, but still 6 orders below the density of air. So it's really truly amazing. The cold gases have now reached a situation where we have sort of small liquids. Honestly, sort of, I think one of the heroes is not here, but he's very close by. Dmitry Petrov predicted such things in 2-component BECs and actually gave a reason how to stabilize these systems with LHY corrections. In this case, he's on the safe side, and this is all nice. And actually, sort of Laetitia Teruel, who was here a PhD student a long time ago with Christophe Salomon, actually they did these experiments. On the dipolar gas side, this has also been seen, but I think there it's not so well understood. So what we need is, we need something that in a way stabilizes these things. Why doesn't the stuff sort of collapse completely? Well, we have to look at what is called the effective potential as a function of the order parameter. So it's in technical knowledge, technical terminology, that's sort of the Coleman-Weinberg potential. Of course, at 3 level, this is just sort of Ginzburg-Landau, mu times psi squared plus chi times psi to the fourth. But the effective chi is negative, so the psi to the fourth term is negative. So that's disastrous. So we need higher order terms to stabilize that. And so so we start with some minus mu times psi squared plus chi effective over 2 psi to the fourth. But then we cannot, I mean, if we stay here, then nothing. This is not stabilized. So we need additional terms. And so let's add, and so I add 2 possible terms. One is, I write it in the following way as 2/5 lambda to the 5/2 times psi to the 5th. This is what people assume to be the cause of it, LHY. But there's another possibility. It could be lambda 3 divided by 3 divided times psi to the 6. This is a repulsive 3-body. This is actually, this example is something that you can work out essentially completely. And that has been done by myself and by Damson in the recent years. That's under control. If you have repulsive 3-body interactions, and for instance, if you have a Bose gas where you go through 0 of the scattering length, then there's this lambda 3 is proportional to a quantity which is called D, the so-called 3-body scattering hypervolume, was introduced by Sheena Tan in 2008. And the imaginary part minus the imaginary part of this L3 is square root 3 over 2 times is related to 3-body decay, the 3-body, the imaginary part. But we need, here of course, we need the real part of D is positive. That needs 3-body repulsion. In this case, for this problem, you can work out everything. And that has been done by myself and by Son. And that happens actually if you look at how do you go from a situation where, sort of, for instance, if you could change the interaction potential between cold gases such that basically they don't have any bound state anymore. At that point, this comes in. Here, it's the LHY. And the question is, I mean, what is the LHY with dipolar gases? So what do people do? Well, and this is something that, I mean, LHY for dipolar gases. So what is this? So this needs to be, if this is positive, we are safe. But the question is it true? Well, you can express it in terms of that's 4g over 3 pi squared times g times mg divided by h squared to the power 3/2. That's the LHY term as you have shown in this description. So that's nicely positive. So the major thing is what's happening with dipolar interactions. Well, what people say is the only it's multiplied by some factor called Q5 of epsilon dd. So if you look at the derivation of this, it's very mysterious, but I mean, it's a trivial story, but it's wrong, to be honest. See, I mean, this stuff comes from the one loop correction to Bogolyubov. The one loop correction to Bogolyubov, at the end of the day, so you have to renormalize quite a bit to get this. At the end of the day, you get something like an integral q over epsilon q squared. Now you see this. goes like, okay, a angular integration times an integration on the magnitude of q, which involves q squared dq, and then this is c squared of q times q squared. It comes all from the low energy physics. LHY is the 0-point energy of the Bogoliubov excitations. And as in the Casimir effect, it's a low energy phenomenon. The whole effect comes from Q going to 0. That makes it so complicated. And then you see, okay, I've told you for dipolar gases, the square velocity depends on direction. And so you get this. And so this function is just the integration of the direction. That's all. That's very simple. But then you see this beast becomes complex for epsilon dd larger than 1. So it's completely ill-defined. The community, in my mind, well, not in my mind, that's just a matter of fact. The community just ignores it. They just work.
They just work with the real part.
They just work with the real part. I mean, it's not. I mean, okay. I will say nothing more about this. I mean, everyone can do sort of a theory as he likes. It's not the kind of theory I would like to do. So what people do is, to explain all this, is what they called, and you find hundreds of papers with what is called extended Gross-Pitayevsky. So they just replace in the Gross-Pitayevsky equation now. So the Gross-Pitayevsky equation has a cube nonlinearity. You replace this by g times, let me get it right. Plus, and then there's some factor here, and then there's an a to the 3/2, which comes from essentially this then, and then some epsilon dd, and then psi times psi. So altogether you get a 4th order term in the equation of motion. That's extended Gross-Pitayevsky, and it works. That's a deep question. I mean, it works to a reasonable extent. Why? I mean, it's completely off for me. I mean, it's not. It has no foundations, to be honest. Well, it provides. So I mean, it gives you, for instance, a simple estimate for the density of this liquid. For instance, I have it on this sheet, which actually agrees with what is observed. It gives you reasonable agreement for, or a reasonable critical epsilon dd for the onset of this supersolid formation. So, so people just use it as a memory. I'm sorry, this is not the kind of stuff I want to.
So the Q5 becoming complex.
Yes.
Do people understand what's the cause? What causes it being complex?
Sure. Epsilon q squared is negative. That's the point. I mean, so this is the c squared of q has this form 1 plus epsilon dd plus 2 pi. That's a formula which I had in the beginning. So this stuff becomes negative.
Okay, so clear, then the mathematical origin. Then the question is, at some points you also mentioned that you have to introduce some cut parameter to cut off.
Okay, that's a short distance cutoff. Here, this is long distance physics.
So I'm saying, of course that's completely irrelevant here, but then.
Yeah, that's.
So does it mean then that you have to, your theory may be restricted, or the theory here has to be restricted to some values of epsilon dd such that that condition doesn't arise? I mean, can you push it this to really be
Well, I mean, this epsilon dd, which comes from this condition where things become unstable, is larger than 1. There, the sound velocity is squared or negative. This gives the complex stuff. And it's just you're expanding around the wrong vacuum, if you wish.
Right, so that's what I was asking.
Yeah. So I don't know. A few words about the next thing is sort of the supersolids. I mean, that's also, now we are not, go away from this nasty stuff with this instability, squeeze the dipolar gases into pancakes. Then things are nice, but new phenomena show up. So this is the pancake story. Sort of this is what I call weak crystallization to supersolids. That's something which is extremely interesting, and I think is a bit better understood, but also not really very well understood. I truncate the VDD to h bar omega c much larger than truncate to 2D in the sense that I have a strong transverse confinement. I have pancakes, and I'm only sitting in the lowest sort of transverse excitation. So basically, this picture up there on the right, just squeeze it to a pancake. Then the VDD of Q now is Qx, Qi only, looks like the following. Q times LC. It's positive here and becomes negative on a scale of the order of 1. So that's fine. So that means the dipolar interaction itself is already repulsive, at least at long wavelengths. So that's fine. This was, I mean, the first to point that out was Uwe Fischer in 2006. So you're on safe grounds. But of course, the danger comes here. You get negative V of Q at shorter distances. And what I point out here, this LC, I mean, the length, the characteristic momentum scale where sort of the potential becomes, Fourier transform becomes negative, is set by the confinement length. It has nothing to do with the interparticle distance. That's very important because, I mean, that's an unsolved problem. I mean, if a superfluid freezes, I mean, where does it end up? Does it end up in a supersolid, or does it end up in a Mott insulator? Helium-4, when helium-4 freezes, it ends up in a Mott insulator, actually. And it's not a supersolid. All these speculations are nonsense. But so, OK, that's fine. And of course, then this negative part gives rise to, now if I do again Bogoliubov theory, tells me that I can write the excitation energies also in terms of the static structure factor of the system. That's sort of the exactness of the Feynman single mode approximation for arbitrary Q. Looks like on this one. So we are safe here. That's fine. But, of course, we are not completely safe here in the sense that, OK, if I crank up the epsilon dd, I mean, this roton moves down. And so people already quite early on, Zoller, Levenstein, Schliapnikov, and so on in 2003 or so, said, okay, that's a precursor of some sort of, in a way, crystallization. And, well, I think there is, of course, a bit of sort of, there's quite a bit of good physics there, but it's not, my claim is that the roton instability never happens. It certainly doesn't happen in helium-4. Helium-4, you have a roton, but if you press pressure on helium-4 and look at whether the roton goes down, it hardly moves. And when it becomes a solid, it just jumps from a finite roton minimum to a solid. The question is, I mean, what's going on here? So the question is roton instability. Does it happen? So if the roton gap here, does that really go to 0? So I think it does not happen. I don't have really time to discuss this. I will just say two things here. One thing is that, okay, this is the Leggett inequality. I mean, that was in a way forgotten. This is from 1970. It was a paper that was long forgotten, essentially, or not forgotten, but only experts knew about it. In recent years, it has become, okay, wow, that's something. Whenever you have a superfluid with a finite density modulation, so density is not uniform, then what you can show is, or what Tony showed, is that the superfluid fraction, even at 0 temperature, is bounded above by average density divided by unit cell, if you have a periodic density, d divided by dx over n of x to the minus 1. So you have not seen it before, sort of, because it's not, you have to integrate the inverse of just the density, simple microscopic density over a unit cell. And so you can, a very simple expression for that can be written in the following way, that is roughly, it gives you sort of the visibility. If you have a density profile in a periodic system which looks like that, then, so the unit cell from here to here, then I have a maximum and a minimum. And the visibility is, as usual, maximum minus minimum of density divided by the sum. If I have a situation like this, with a little density in between, this visibility is close to 1. And then this Leggett bound tells you the superfluid density can certainly not be larger than this, so it becomes small. And so what is actually not so well known is actually sort of, you can write it in the, it's a, of course, lower bound, upper bound on Fs is a lower bound on Fn. So Fn is larger than the 1 minus, and if you work it out for helium-4, solid helium-4, the Leggett bound gives you that solid helium-4 has to have, in the ground state, has to have a normal fluid density which is larger than 84%. Well, actually, it's 100%. It's not superfluid at all. But so this actually was, and this is not very well known, worked out from numerical data on the microscopic density profile by David Zeppeli in 20 years ago. So this is, but what this Leggett bound tells you is, okay, it's the interesting things you look at. I mean, if you want to have supersolids with sort of a reasonable value of the density contrast, you better look at something where you have a density profile which is not really that extreme, but is something like weak crystallization. That, of course, favors. But of course, this bound never tells you whether you are. It's just a bound. And so the other thing is I wanted to this is something that we have worked on ourselves. And the freezing transition is treated, again, with this extended Gross-Pitayevsky. And it gets results which, I mean, okay, are on reasonable agreement with experiments, although experiments are not that really precise. But okay, it's quite remarkable. Let me say something about the hydrodynamic modes for sort of smectic type order. Smectic types order means, and this is just what is shown on the sheet, you have order, just a density wave along only one direction. And so there must be a phase diagram where, or there is a phase diagram which in detail hasn't really been calculated, where you say you have temperature here, and you have sort of the strength of this dipole-dipole interaction, which in the pancake configuration is mostly repulsive, but still has attractive components because it's still allowed that dipoles sit on top of each other. So there must be a TC where we have a normal fluid above here, a superfluid down there, and then there's a second line which must cross this. Where we have, I call it a normal mass density wave. A smectic liquid crystal is a mass density wave incommensurate with the system, and a superfluid mass density wave. And that's what we call a supersolid. I mean, the definition of supersolids is sort of not universally agreed on. I mean, certainly everybody agrees on that we had to have broken translation invariance and broken sort of gauge symmetry, if you wish. But then, I mean, Wolfgang Ketele was always saying, well, then, I mean, what about the vortex lattice? That also breaks translation invariance and thing. The answer is the vortex lattice disappears if you go above TC. It's a modulated superfluid. You can, depends on your taste. Here, what I believe is that, I mean, I assume this order is also there in the normal phase. And then you get a phase diagram like this. And this line, I believe, is first order by quite general arguments. But this has not been really seen or, I mean, demonstrated. It's very hard, sort of, I mean, maybe if it's in the finite, in the small systems or so, this is not so clear. And then you can count sort of the number of modes. I mean, this is something that we have here. And I mean, I just want to, in the normal fluid, we have sound and a few diffusive modes. If I break translation invariance along one direction, it was actually Pierre Gilles de Gennes who worked out these things more than 50 years ago here, and Paul Martin actually on sabbatically here at Orsay. There is a so-called, there's a diffusive, if I look at propagation along the direction, there's a diffusive permeation mode. So interestingly, you add a diffusive mode by this. And here, what's happening in the supersolid, the defects propagate like sound. So there's a new propagating mode, C2. This is something that was predicted by Andreev and Lifshitz in the 60s. And the major thing is that, and this is the last equation I write down. If I look at sort of density fluctuations in a solid or in a solid or liquid and so, in a fluid, I just sort of express this in terms of gradient of densities. In a structure with a finite sort of structure, I must write times the divergence of mu. plus delta rho of x. So that's, you need there's two ways in a system with a periodic density wave. There's two ways of changing density. Either you change the lattice constant, that's the usual thing, or at fixed lattice constants, particles can hop from one cell to the other. Usually people don't deal with this. This is diffusive in a normal solid, but it becomes propagating in a supersolid. And there's actually indications for this. I think on one of the sheets there's this experimentally, what you see is that the breeding mode in these traps splits into two. But OK, then there's lots of open questions. I am sorry I took too long, but OK. Thanks a lot. I believe that dipolar gases are probably the most complex system that has been looked at so far in ultra-cold gases. The theory, I think, is at a very sort of rudimentary stage. There's lots of things that can be done or should be done, but it's hard. I've written down a few exact things, but I mean, going beyond that is super hard. OK, thank you.
Thank you.